All right, this screencast is going to be on localized winds. We're going to be looking at land and sea breezes, and we're going to determine or explain why it is actually always cooler by the lake when we talk about Lake Michigan. So local winds. These are produced from temperature differences. And these are typically referred to as small scale winds. And a couple types. We have land and sea breezes, we have mountain and valley breezes, and we have Chinook and Santa Ana winds. We are going to be studying land and sea breezes. A land versus a sea breeze. Land and water have different specific heat capacities, right? That's the total amount of heat energy in the caloric value necessary to heat up 1 gram of water to increase its temperature 1 degree C. During the day, land heats up more quickly and forms a low pressure due to rising air. During the day, air from the water sweeps in, leaving a sea breeze. It cools the surrounding area. So if air is rising on land, right, land is going to heat up more than that of water. This is going to rise. It's a low pressure. We've defined low pressure as air rising. Water is going to be filling in this space from the seawater. So we create what we call a sea breeze. So during the day, there's a low pressure over land, and we get what's called a sea breeze. At night, the land cools to lower than that of the water, so the breeze switches in its direction, right? During the night, the process is switched. So here we have the land is going to cool much, much more than the water. The water is going to have the thermal inertia or resistance to cooling. So now my low pressure is going to develop over the body of water. It's going to rise over water, and the air is going to fill in from the land. This is a land breeze. So we have two different features we have that we're looking at. Where's the high pressure? Where's the low pressure? It might be easiest to say find where the water or find where the air is rising. That's your low pressure. So during the day it's over land. During the night that's over water. Wherever the low pressure is, the wind is going to be blowing towards it, right? High to low pressure. Winds always blow from high to low pressure. So here I can quantify it. I can look at this from a millibar standpoint, from a pressure gradient force. So a sea breeze, remember, when we talk about by Lake Michigan, we would call that a lake breeze, but it's technically a sea breeze. I mean, it's just a smaller scale sea breeze, a lake breeze. Same effect. So here I have a value. I have between 1,008 millibars and 1,016 millibars, so we'll call this 1,012. And this is higher pressure. Notice my millibar value here is between 1,004 and 1,008 millibars. We'll call that 1,006. This is a difference of 6 millibars. It's going to blow from high to low. This is my sea breeze. I go from high to low. Low pressure, it's going to warm up. It's going to rise. It's going to come back in this convection current. This would just be one convection cell. The high pressure is then going to right up at elevation. It's going to come back. It's going to cool. Then it's going to sink as it travels back toward the water. We just create this, during the day we create this convection cell generating a sea breeze. During the nighttime, this switches. Notice my pressure gradient force is going to be, I have my 1,012 millibars over land, and I have 1,006 millibars over water. High to low, this is going to be my land breeze. Notice the direction is from land to the water. I have a convection cell generated that's actually switching directions. Now what's interesting, you can actually get a certain point in time where there is no pressure gradient force, where they are balanced, and it would actually be calm for a little while. That was implying that if there's no pressure gradient force, there is no wind. So here, wind measurements. The two different measurements we study or we work with in class are direction and speed. The direction, winds are labeled from where they originate. A north wind, this implies that it blows from the north toward the south. So a southerly breeze would be from the south to the north. And an instrument for measuring the wind is called a wind vane, and here's an example of a wind vane. In wind measurement, when we measure direction, direction is indicated by either, you can use a compass, north, northeast, we can say south, southeast, west, etc. Or it could be in a scale of 0 to 360 degrees, right? Just creating a unit circle. The prevailing wind, this is the general direction in which the wind comes from most often. And wind speed, this is a cup anemometer. So this here would be kind of a semi-wind vane. It tells you direction, but this would be the anemometer. This is just simply would have a circumference as it makes a rotation, and you could calculate that distance, or well, circumference is a measurement of distance, in some unit of time, and you could just convert that into like miles per hour. but that's what speed is measured in. There you have what we're studying at this point are localized winds. These are small scale winds, and we are calling them land and sea breezes. Remember, by the lake, it's a lake breeze, and it is always cooler by the lake.